Welcome back. So we have been discussing CSI-RS, okay, and what we discussed in the last class was we discussed CSI-RS up to 8 ports, and we'll finish discussing the CSI-RS today, and we'll learn about MIMO transmission, okay. So if you recall, we were discussing MIMO, okay, and then we digressed from MIMO and started learning this different kind of CSI-RS, different kind of reference signals, okay, and one primary reason for this different port reference signal is MIMO, okay, right? Otherwise, you don't need different port transmission, okay. Now, after learning in detail about these different kind of reference signal with different number of ports, you will be able to appreciate MIMO better, that's why it is implemented the way it is, okay. So this is the agenda of today's class, okay. So this is a quick summary of what we learned in the last round and where we stopped. So here we are learning it for 8 port CSI-RS, okay, and these 8 port CSI-RS are created using CDM, FDM and TDM configuration. Example 1 is basically 2 port CDM and then combined with 4 FDM, okay. 2 ports and then 8 ports are created using FDM, okay. Example 2 ports in CDM and then rest of the 4 ports are divided amongst FDM and TDM, right, okay. 2 CDM, then this is 2 FDM and then replicated to give you again 2 TDM to give 4 different ports, okay. This is an example of 4 CDM combined with 2 FDM, okay. 4 CDM over this and replicated over 4 using FDM, okay. And then this has a density of 1 resource element per antenna port per PRB, okay. 8 resource elements per PRB are using to create 8 ports, okay. So this is the density, okay, right. Now CSI-RS is configurable such that it may occupy a part or a whole of bandwidth, okay, because channel needs to be estimated over all the relevant PRBs, okay, and the example which we have taken, it is only for a per PRB. So you see the resource elements being used for CSI-RS, okay. So if it is 8 port or if it, so you use 8 resource element per PRB. If it is 32 ports, we are using 32 resource element per PRB. It's a, as I said, it's a humongous requirement, okay, right. So doing it over entire PRB or entire bandwidth part, it's a costly affair, but that's what you'll have to do, okay. So and this is another fact, the starting PRB and number of PRBs of CSI-RS are configurable with a granularity of 4 PRBs, okay. So if you have to like, so this is, constraint is that minimum CSI-RS bandwidth is 24 PRBs, so you need to estimate over a minimum of 24 PRBs. After that, you increase it with a granularity of 4 PRB, okay, and you can, with that you can go over entire bandwidth part also, okay, right. CSI-RS, as we have seen, okay, has a density of 1 RE per antenna port per PRB, right. That's what these are the examples we took, okay. We'll look at that, and but the density can be increased. That's the point I made in the beginning, okay. Can be configured for 3 resource element per antenna port per PRB, or it can be reduced 0.5 resource element per antenna port per PRB, okay. Either it can be increased or reduced depending on how your channel is changing, okay, right. If the channel doesn't change across, let's say, frequency, right, so what will you do? In one PRB you will transmit, and another PRB you don't transmit CSI-RS, so the density is reduced, correct, okay, right. If the channel is changing, so what you do, increase the density, right, you make it, you can actually make it up to 3 resource elements, okay. So for each port you can increase, or like you can basically increase the number of resource element over which these pilots are being transmitted, right, okay. Just to like, how will you increase the density over here, okay. 8 port, transmit 8 port, let's say you have to make density as 2. One you are transmitting here, one you transmit in this part. The whole structure you replicate over here, right, okay, for some reason, or you transmit over here, then you basically interpolate, right, and then you replicate it over here, it becomes 3 RE per antenna port per PRB. That's the point I'm making, okay. The user is moving fast, you want to estimate, then one here, another here. You have the like flexibility of transmitting it like that, okay. So right, that's the point, okay. Now, having studied this structure, okay, that was mostly like how they are designed, okay. How frequently they are transmitted, that's what it is, the time domain structure, and it is similar to SRS, okay, right. Why it is similar to SRS? Because what is CSI-RS? CSI-RS is the downlink counterpart of SRS, right, okay. They are not transmitted with data, correct, okay. So you can configure them in 3 different ways, and those 3 different ways we discussed in context of SRS, okay. Periodic, aperiodic and semi-persistent, you will see the same structure, okay, right. So for periodic CSI-RS transmission, again RRC configures it, goes on, right, okay, that is the periodic CSI-RS transmission, okay. Then semi-persistent is similar to this, but MAC has to get into picture, okay. It will be configured again by RRC, but it will be activated by the control element sent by the MAC, okay, and then again it will be deactivated by the control element sent by the MAC layer, right, okay. Then what is this? This is the aperiodic, okay, correct. So this is basically what are we saying here, that this DCI, this is enabled by the DCI, okay, configured by RRC, but enabled by or disabled by DCI, okay. So enabled or disabled by DCI means that DCI will say please transmit CSI-RS for this much duration, that's all, okay. Again, if it has to be CSI-RS has to be basically triggered, then DCI has to be sent again, which will tell that the CSI-RS has been transmitted, okay. This one, it is basically what is it telling, okay. Then we did not discuss in context of SRS. What is this same slot receptions? What is this DCI telling? That if the slot offset is 0, it means that the CSI-RS is being transmitted in the same slot, okay. If the slot offset is 6, it will be transmitted after 6 slots, that is what it means, okay, right. So that period is configured for CSI-RS, we will see that, okay. But this is broadly the idea, right, and I am not going into detail because we have discussed this in context of SRS anyway, okay, right. So this is similar to SRS, as both of them are transmitted independently of data, primarily to collect the channel state information, okay. One is for downlink, other one is for uplink, okay. So for periodic and semi-persistent CSI-RS transmission, okay, a device assumes that a CSI-RS transmission occurs every nth slot, okay, is the period, okay. So for how much, what is the period between the CSI-RS transmission, okay. What are they saying? Every nth slot, where n can be between 400 to 640. These are the number of, this can be the period. So and is also configured with a specific slot offset for the CSI-RS transmission. I will show you that, okay, that the picture will become clear, okay. So how is it configured? What is this picture showing? So here the CSI period is 5 slot, okay. So CSI is coming, RS is coming every 5th slot. That is what I said, n can be between 4 to 640. So this is n, right, okay. And what do we mean by offset? It is here only you are like this is, let us say this is what is that, you are configuring over here, okay, and the slot offset is in the same slot you are sending it. So the offset is basically 0, okay, period is 5, right, okay. What about this? Here again the period is 5 slots, right, but you configured it here, this offset is 3, that is all, okay, right. So see, this is same period but different offset, okay. Here same offset but different periods, correct, okay. So here the period is 10 slots, but you are configuring it here with an offset of 3, okay, right. So that is the configuration of CSI-RS, okay. Now again CSI-RS, as we understood for SRS, that they are basically QPSK modulated, okay, and each, that is what this bullet is telling, each CSI-RS resource element is QPSK modulated, which is generated as follows. This is the formula we saw, okay, right. So this is the CSI-RS QPSK modulated. What is C? Again remember this, scrambler, okay, length 31 gold sequence, we know how it is done. So I am not going to go into details of this, but this is how the CSI-RS will be QPSK modulated. Okay, generated with different seed value for each OFDM symbol of a slot indexed by 0 to 13. This is how you initialize this scrambler. Okay, I am only telling you briefly how it is done. The exact formula, okay, you have to look into the standard. Okay, that's how it is done. Okay, right. So what have we learned? Where are we? We have finished discussing CSI-RS. Okay, right. Key points over here are that CSI-RS ports have multiple use cases. Okay, we have at least seen two. One is for estimating wherein the precoded channel, UE estimates the precoded channel, okay, using the precoded CSI-RS sent by the base station, right. Okay, so there the number of port requirement is small, okay, because the precoded channel is compressed. Then second one is unprecoded channel, that is typically used for FDD system. Precoded channel is used for TDD systems. Okay, then this unprecoded channel, because it is not compressed, you have to use larger number of CSI port, which is dependent on the number of transmit antennas. Okay, in practice. Okay, right, there is a caveat there also, because if you look at it, we are defining 32 antennas and we are defining 32 ports. What is the dimension of compressed channel, uncompressed channel you can estimate, right? It is basically H should be NU cross NT, right? That's what you can estimate. That essentially means that NT can be a maximum of 32, right? But base stations are being designed with 64 antennas also. Okay, how do you estimate the channel of that? Okay, I am not getting into the details because I can briefly tell you so that you have some picture of it. See, like our system, okay, is designed for a 64 antennas, okay, but CSI-RS is only 32 port. Okay, now base station compresses this 64 antennas channel to a 32 port channel. How does it do? It uses a fixed precoder which doesn't depend on the channel. Okay, right? So those precoders can be designed without channel information. Okay, right? See, I can design the system for 128 antennas also. Okay, right? That standard doesn't restrict me to design or install the higher number of antennas. But what it restricts is that I can estimate channel only for 32 ports. Okay, right? So if you are designing a 64 antenna system, okay, so you use a fixed precoder to compress a 64 antenna channel to a 32 antenna channel. Okay, you can design a precoder, right? Okay, which does not depend on the channel information. Okay, so that's how it is typically done. I'm just leaving you with that. Okay, that you should not think that with a 32 port CSI-RS you can only design a 32 antenna system. No, you can design a higher antenna system, but you'll have to use something called a fixed precoder. Okay, right? So this is the CSI-RS. Okay, now after discussing this, what we are doing here is we'll see how MIMO is implemented in the standard. Okay, right? So again, before we go there, CSI-RS for TDD you need a lower number of ports, but again with the caveat that you should have done the TDD calibration. Okay, right? If you are not able to do a TDD calibration, then you again switch to unprecoded CSI-RS transmissions so that UE can estimate the downlink channel, UE can decide the precoder, okay, right, and then feed it back. Okay, we'll learn that also, how that process is done. Okay, so this process of UE estimating the channel, feeding it back is commonly done for FDD, okay, but it could be done for TDD also if you are not enabled, if you don't know how to do TDD calibration. Okay, I'll stop with that. Now we'll start discussing how MIMO is implemented in the standard. Okay, so I'll recapture it based on how much time we have, then we'll continue. So this is our system model, right? Okay, what we are doing here is that this is the precoder, this is a precoded transmission. Okay, NL number of layers. Okay, V is the precoder, either the base station knows it or UE feeds it back, correct? Okay. Now, so what will this precoder do? It will take in NL layers and then it will map it to NT antennas, correct? Okay. Then you transmit the signal over this channel, you receive it over NR antennas and then multiply it with the receiver and then you get these NL layer backs, right? Remember this picture, okay? So what is this? Why they have to h x tilde plus n? What is x tilde? X tilde is precoded signal, V of x, and then it becomes h tilde of x plus n, correct? Okay. At the receiver you multiply it with W Hermitian y, right? So we are very comfortable with this. For TDD system studied till now, G node we design the precoder V and decides the rank. Rank is basically number of layers. If it knows the channel, it knows the rank, okay? So dimension of V is NT cross NL, input is NL layers and the output is NT cross 1 vector. What do you get? What is this? What is the output of this precoder? V of x. What is this? This is a vector, right? And what is the dimension of this vector? NT cross 1, correct? Okay, right? Rank is equal to the number of layers, equivalently the number of parallel streams which are being transmitted on the same resource element. Okay, fine, this is only the recapturing, okay? And UE can employ any receiver, right? We discussed one receiver, what was that? SVD based, okay, right? And there are other different kind of receivers which are commonly used, okay? We are not going into the details of this, but zero forcing also we have seen. What will zero forcing do? How will the zero forcing receiver look like? Instead of like WH, what will you do? H tilde inverse, right? Then also you will, if you do H tilde inverse, if you multiply Y with H tilde inverse, what will you get? Again you will get X, but this noise will be different, that will degrade the performance, okay, right? There are other different kind of receivers, MMSC, SIC, okay. MMSC is minimum mean square. This is minimum mean square successive interference cancellation. I am introducing you to this because the way this MIMO architecture is defined in the standard, it uses this idea also, okay. So I am just like telling you that, okay. Then there is maximum likelihood receiver, okay. We briefly touched upon it, right. Maximum likelihood in the beginning of the course somewhere, okay, right. So this is our system model, okay, fine, right. This is what we have learned, okay. Now what we are saying here, don't look at this, okay. I will tell you what is happening over here. So the configuration what we are assuming here is the base station has NT is equal to 64 physical transmit antennas, physical antennas, okay, right. So H and that it is NU cross NT, this is that NT, okay, right. So what are we saying here? So if NL is up to 4 layers, okay, what do we mean? If the channel rank is 4, base station knows it, okay, whether it is a TDD or FDD system, okay, right, we assume that base station knows it now, okay, right, okay. So what happens in this case, how MIMO is implemented, that is what you see, phi receives one transport block. If it is MIMO transmission is up to 4 layers, okay, MAC will send only one transport block, okay, they send only one transport block, fine, okay. So what happens, okay, so let us look at this, this is one transport block, correct, okay. This transport block undergoes the processing, we understand this processing and I have taught you till here, right, okay. This is what am I saying here, at the end of this what you have, one modulated code word, complete, right, okay, segmented, all that is done, concatenated, scrambled, modulated. At the end of it you have single code word, right, concatenated code word, okay. Now the layer is 4, okay. If you remember the way the transport block size was calculated, number of layers also play a role, right, okay, right. If number of layer is 1, the number of resource blocks let us say are 10, okay, correct, what will happen, okay, right. So the transport block size, if the number of layer is 1, let us say it is 100, just for example, okay, when compared with NL is equal to 4, MAC will send a transport size of 400, okay, even though the same PRB, over 10 PRBs you need to transmit. Okay. Why? Because now with 4 layers, you can transmit 4 times the data, amount of data which you can send with NL is equal to 1 layer over the same number of PRBs. That's what we have learnt in all this MIMO processing, right? Correct? Okay. So the number of the parallel layers which you can transmit over same number of PRBs, right? Okay, that's what is MIMO. Okay. So what are we saying here? The 5 processes this transport block to give one modulated code block. Till here there is no distinction. Okay. Now after that you see this layer mapping block is coming. Okay. So layer mapping block takes these modulated symbols which were denoted as D. Okay. Right. Q is this index. What is the index? What is this Q denoting? Is the transport block index. Okay. Q is 0. Okay. So it will take from this single code word as input, layer mapper, and then what will it do? It will demultiplex this DQI into 4 layers if NL is 4. Correct? Okay. You get this? What is happening? Okay. One transport block, the size of transport block was dependent on the number of layers, of course. Okay. Right? If it is NL is equal to 1, then this layer mapping block will only be a pass through. Correct? Okay. Right. So if it is 4 layers, this you get a 4 layer. Okay. Then there is a precoder. What will this precoder do? We have learnt in great detail. It will take 4 layers and map it to 64. What is the dimension of V? 64 cross 4. 4 input, 64 output. Because what is 64? 64 is the number of antennas. Correct? Okay. Right? So that's what is happening. So it precodes. Now how many such resource block mappings you will have to do? We have learned this till we have avoided this. What was happening? Resource block mapping, single and then CP addition. Correct? Okay. Right? So we were creating only one resource block, mapping one IFFT, one CP. Now how many such processes you will have to do? You have 64 antenna. So you take this precoded signal. What is the output of, what is the length of this precoded signal? Each one of them is a 64 cross 1 vector. Right? If MIMO was not being done, what was it? 1 cross 1. You are taking 1. You are doing you are mapping over one resource block grid, taking IFFT, CP, then doing over one RF chain. Right? Okay. Now what, depending on the number of antenna which you are assuming it to be 64, you take this first element of this precoded vector, map it onto first resource element grid, pass it onto the DAX and the RF chain. Take the second one, take the third one, you have to do this for 64. Look at the complexity of doing it. Right? This is basically the hardware complexity. Right? And the following. You will have 64 RF chains. You will have 64 into 2 ADCs and DACs, because for each chain you need 2 ADCs and 2 DACs. Correct? Okay. So that's what is happening. Okay. So this is the complexity of doing MIMO. Okay. In terms of hardware. Okay. Because this is simple. This is simple. Yes. To get this, you know what is required. Right? Okay. To get this precoder information, all that CSI-RS, whatever needs to be done, it has to be done. Then only it can be enabled. Okay, that's why I introduced you to that. There's only one block. Okay, but the underlying complexity of getting this information is huge. Okay, so what is happening here? Okay, so what is this? The output of this precoder I am writing. Output is layer mapper I am writing is being mapped. You take this, right? I is running from 0. Okay, how many layers? 4 layers. Okay. Right, so this is layer 0 will be 0th symbol, layer 1 will be first symbol, layer 2 will be third symbol, layer 3 will be fourth symbol, and then you again go back, there will be 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th. That's how you are creating 4 layer from the single transfer block. Right? See this processing, okay, MAC is sending only one transfer block if the rank is up to 4, 1, 2, 3, 4, okay, single transfer block. Then after that, number of layers are created at this stage, right, okay. So, and that's how this demultiplexing is done. I will run from, I will keep running, I is the running index, okay. So every 4th symbol becomes 1 layer, that's what it means, okay, if the rank is 4. If rank is 2, every 2nd symbol becomes 1 layer, okay, right. So it will be, if rank is 2, it will be 2i plus 1. This is 0th, this superscript is 0th transfer block, because the rank is more than 1, you will get another transfer block, so this index will be from 0 and 1, right, okay. So for this 0th transfer block, which you physical layer gets for a rank of 4 up to a rank of 4, this is what will happen. You understand all the superscripts, subscripts, okay, right. So this is I, the running index, 0th symbol of layer 0, 0th symbol of layer 1 is basically the first symbol of this modulated transfer block. 0th symbol of second layer is the third symbol, okay. Then the 0th symbol is basically this is then 0th of 0, first of 0, it's only the index, okay, right. So M layer symbol, okay, what will happen? Number of modulated symbols per layer will be how many? If the rank is 4, you are taking those symbols and demultiplexing, okay. So the number of symbols in each layer will be the total number of symbols divided by the rank, correct, okay. So that's what it is. So in this case it will be M0 symbol by 4 for 4 layers, okay, right. So, and since we considered NT is equal to 64 physical antennas, okay, the chain will have 64 resource block mapping, that's what I said, okay. 64 IFFT you will need to take for each of this, because you are creating 64 resource grids, okay, and you will have CP and the rest of the chain also accordingly, okay. So I think this is what I have for this class. We will continue discussing this. We have discussed it for how many layers, for MIMO transmission for up to 4 layers, okay, right. And why we discussed all these reference signals, okay, just to make you understand, okay, what kind of complexity is involved in enabling MIMO, okay, right. This is not, so this reference signals, okay, the number of ports increases, okay, for MIMO transmission, but you have to like understand that even if the MIMO is not there, okay, let's see SRS, all these transmissions need to happen, okay, even if this block is not there, because SRS you need for estimating the uplink channel, okay, but in the TDD system then you can infer the downlink channel. CSI-RS you need so that you can find out the MCS and feed it back, okay, right, even for single layer, okay. DMRS you need to send, okay, because it has to be used by the user to demodulate the actual data, PDSCH data, right, and it should be able to get the instantaneous channel. In all these cases when MIMO is not there, all those transmissions will be single port, correct, and depending on what is the rank of the MIMO channel, the number of ports of these reference signals is going to increase accordingly, okay, right. And that's where those reference signals, one of the uses is to basically design these precoders, okay, so that you can use this large number of antennas which you have designed, okay. We'll stop here, we'll continue discussing this. Thank you.